Good afternoon, everyone. So, welcome to today's Samvaad-Talk. Professor Raghuram will be delivering his talk on deep reinforcement learning algorithms for off-policy control and their applications. So, before we start the talk, a brief bio about the speaker. Raghuram Bharadwaj received his PhD from Indian Institute of Science, Bangalore in 2022. His main research interests are in the areas of reinforcement learning, deep learning, machine learning, game theory, and multi-agent learning. He received the Best Student Paper Award at the International Joint Conference on Neural Networks, IJCNN, 2022 in Padova, Italy. His PhD thesis focuses on developing reinforcement learning algorithms to solve off-policy multi-agent problems and apply these algorithms to the smart grid setup. He received a special commendation certification in recognition of an outstanding doctoral thesis from the Department of Computer Science and Automation, IAC. Before joining IIIT-Bangalore, he was a senior data scientist at Mindra Designs Limited, Bangalore, India, from November 2021 to November 2022. So, we welcome Professor Raghuram. Thanks for agreeing to give the talk and welcome again. Thank you.
Thank you, Professor Vishnath. Also, thanks to Samvaad team, Professor Amrita, Professor Sujit, and all student volunteers for organizing this event. Good afternoon, everyone. So today I'll be talking about parts of my research. I'm not presenting one particular research as such, but multiple facets of it in a logical and coherent order. Right. So, yeah, I wanted to do it in a slightly non-linear fashion. I'll directly not tell you what is RL until second part. Before that, I'll start with an application of an RL to show you what can be done as a sample, right? And then the application I chose is UAV navigation. This is our recent most work. So using human feedback. And then I'll discuss or ask what is RL. And then finally, we will see, a very theoretical development of algorithms in off-policy problems, right? So this is environment, right? So we have an UAV, unmanned aerial vehicle, and you want to navigate it in an environment. So this is a sample environment taken from the simulator called Gazebo. Some of you who work in robotics must be aware of this environment. So this is essentially our UAV, and these are the vertical bars are the obstacles. And take a very simple scenario, right? Your objective is to just make this UAV navigate this environment without colliding the obstacles. Suppose you know the entire plan chart like this. If I am giving you this, then it's essentially a rule-based system, right? You can say go straight for a few meters, then take a right, take left, and so on. If you know the map of environment, if it is given to you, if it's known to you a priori. But often these are uncertain environments, right? Take the same example. Suppose you pre-wire, all the instructions. Suddenly I change a very small obstacle. I move it by left or right by 1 meter, and it's definitely going to collide, isn't it? Because you didn't plan for it. It's a very rule-based system, right? So when environment or map, we call environment in RL, essentially, right, is known, then any rule-based navigation system will work. You don't need any intelligent algorithm. But of course, we all deal with uncertainties. We all deal in environments which is not mapped out, which is not known, and still have to make the UAV do whatever you want it to do. So what do? We want to train the UAV, right? Every time you can't say this is environment, you map it some actions, and then environment changes. Again, you have to go and, do it. For example, say you're learning to cycle, right? Or teaching someone to ride a cycle. You're not going to say in Malleshwaram you drive like this, in Electronic City you drive like this, right? You just train the child on a particular road and ask them to generalize. So it's like this, right? You need to train the UAV, and the paradigm we use is RL. So what we do is we give some numerical values to train it. This is a simple application. You want to avoid obstacles. What do? You give a reward for no collision. Every time it takes an action, if it's not colliding and falling down, you say job well done, and you give a positive reward. And if it is colliding, you say this is bad. You are incurring a penalty, and you give a negative reward or a penalty, and say that this is bad, right? And let's call this function, reward function, where if there is no collision, it's a positive number, And if there is a collision, it's a negative number, R1, right? Over time, this is important. Over time, UAV learns to navigate safe. What do you mean by over time? Just because you gave a reward doesn't mean instantly it starts working, right? It first explores. It takes various actions, keeps falling down, says, okay, it is getting negative reward. And then it says, I need to maximize my reward at each point. What do? You keep over time through learning and training, it learns to navigate safely. Just like how we learn a cycle. We fall down. We say that it is assumed that falling down is bad. So over time, you try to ride in a way where you will not fall down and go in a logical and correct roads, right? So that's what happens with UAVs. Excellent question. So I didn't go into the details, but here assume that at every instant you take an action, you didn't collide, well done, right? You get a positive reward. And next time you collide, you get a bad reward. And so that's a good question as well. Of course, I didn't go into the details. This problem here we are dealing is partial observability because you can't get an entire environment. So that's an entire different framework of QMDP, but ignore that. Let's say you get full environment visibility. Yeah. Now, I'm adding one more task. Along with avoiding obstacles, I want the UAV follow this pattern. These are called waypoints. I want UAV to pass through these waypoints, right? For example, take an application of having a drones in a wildlife sanctuary, right? So these waypoints can be like animal, capturing animals, the hub of particular animals, right? Here you can have set of lions and other animals, not this close in you. But yeah, you can have these animals here, and then you want to navigate the UAV in such a way that, number one, along with avoiding obstacles, it needs to pass through these waypoints. Again, need to train it autonomously. What do? The only language we know is reward function. We say that if you pass through this waypoint, well done, you get a positive reward. If not, negative reward, right? Now, that is not the only objective, right? This is R2. R2 is saying you need to pass through the waypoints. R1 is avoiding obstacles. When you want both, what should you do? Combine them, right? So essentially, so we want a reward function that does both. So you have some function, some linear combination of R1 and R2. In normal language, it's like if you avoid obstacles and pass through the waypoint, you get much higher reward. If you do either of it, you'll get some reward. If you don't do anything, very least reward, right? Looks good, right? In theory, this is what we are thinking. But can you imagine issues that can arise? Because this is learning autonomously. You give a reward function and you're done, right? The UAV has to learn on its own using just that reward function. Can you see any issues in practice? Yeah. That's why we do it in a simulator. Yes, that's correct. Yeah, transferring to real system is pretty difficult, and that's one of the criticisms of RL as well, where it works beautifully in simulation and games because there is no harm in games. But you transfer it to real life, we need to be, there is an entire paradigm of safe reinforcement learning, while at the same time you're doing what you want in a safer manner. Good. Shortest path is not guaranteed. Any other issues? This is what we call sometimes undecided behavior, right? For us, it looks good, right? R1 and R2, you are combining it and you're telling it, but that's what you are interpreting. That's not what agent is interpreting. So imagine, you go back here and suddenly it passes through this waypoint and goes and collides. Right? What happens? So every time it passes through this waypoint, with some probability, it goes ahead and collides the obstacle. So what does UAV interpret from this behavior? Passing through waypoint is dangerous, not good, right? Because after passing through, it is getting good reward, but it is going ahead and colliding into the obstacle, right? So it essentially learns that passing through this waypoint is dangerous, right? So that's the kind of behavior algorithm can learn. I'm not saying will learn. Of course, in an ideal world, theoretically, of course, it will learn to navigate through that and avoid obstacle. But because a lot of complexity is inherently involved in any RL algorithm, like neural networks and stuff like that. So we all heard about, the gradient algorithms are not necessarily converge to your global maximum. Right? It can go and converge to your local maximus. So that's what happens, essentially, if it, most probably, like very high probability, if it passes through one waypoint and immediately goes and collides, and if this experience is repeated, it thinks that, okay, I'm getting very bad reward by colliding. Let's not even pass through the waypoint. Let's avoid it. No, it will go and converge to a local optimal solution. That's the issue, right? So that's a practical issue. I'm not saying it happens always. No, this is a problem in practice. And add moving obstacles now. So you have waypoint navigation, static obstacles. Moving obstacles are birds and stuff like that. So many reward functions. And how do you come up with a reward function that captures all the things and performs optimally, right? So that is what we call as reward shaping. Researchers have spent an enormous amount of time on devising reward functions which can capture all the things optimally. But the consensus is reward shaping is not easy. It's a hard problem. There are solutions, right? In literature, there are traditional techniques like inverse reinforcement. It's like an expert performs something, and from that you infer what is the reward. Because we assume that expert, of course, she or he is an expert because they know what they are doing, right? So from their trajectories or from how they behave, we backtrack and try to learn a reward function. But in this application, right, or in some other applications, obtaining expert trajectories are not so easy. Right? It's like playing a game at a very high difficulty level, right? So easy in the sense it can be costly, both getting experts like that, and at the same time number of samples that you require to converge to your solution. So both in terms of cost as well as your sample complexity. So that's when we have this concept of preference-based reinforcement learning, right? So someone would have, most of you, I'm pretty sure, would have heard about this RLHF, reinforcement learning from human feedback, which is being used in this GPTs and this transformers architectures, right? So where the central idea here is, instead of the reward function construct, so this completely eliminates the construct of reward function, because we agree, or at least I might have convinced you that reward shaping is difficult, right? So if you agree with that reward shaping is difficult, so this paradigm completely gets away with it. It says, I don't want any reward function. Instead, the UAV navigates, collects trajectories, and presents it to you. Hey, these are the two things I can do. You tell me which is better. Did you like trajectory 1 or did you like trajectory 2? Right? And then based on the human feedback, we don't need expert, because we are good at judging two things, right? We might not know how to navigate optimally, but presented two options to us, anyone easily can say, like, this is better than that. For example, look at this picture, right? The UAV has to navigate. There are two paths. It can go left or it can go right. Which is better? Left, because right is an obstacle. It's an end, dead end, right? So one can easily say that, okay, I prefer left over right, right? So this is the input. This is the input that is given to the algorithm. Instead of the traditional construct of reward, you have pair of trajectories given to a human, who then says, I like left over right. And based on this input, right, this algorithm called preference-based RL finds out the reward. Yeah. Excellent question. So this is definitely greedy, right? Who knows, after going left, you have one more dead end. But again, you would see that, right? The UAV presents it to you, says that, yeah. Yes. In fact, I'll tell you one more situation where you are not sure which is better. All of them can be represented. In fact, the kind of the preferences you give doesn't have to be 1-0. It can be a probabilistic preference. Yes, we are assuming the strict ordering of preferences. But no, human is providing this. So the UAV does this maneuvering and gives you two paths So I have taken exploration. So the UAV does what it calls an exploration, right? It explores various options using the actions that it has and then presents to you, okay, I think these are the two capabilities I can do and which is the better. And to answer your question, right? So it can be greedy. That is why I kept telling that trajectories are shown to you. That is, it traverses entire ground and then presents it to you. So you see a video, not a picture. Here, of course, I didn't play the video. It sees a video of what UAV does in two different simulations and then selects, I like this video over there. So in that way, long-term dependencies are also captured. It keeps, yeah, it keeps getting complex. Initially it is pretty plain trajectories and you say this is good and this is bad. It learns something and then you keep adding complexities. So it keeps finding the right path over time. So that's a good observation that, here the reward function is dynamic. It keeps shifting based on the new preferences and new trajectories that the UAV generate. So that's one of the advantages of having this paradigm. Yeah. So what do you think is the most logical thing? Uniformly random actions. Just go ahead and explore, enjoy the environment. Initially, you don't know anything. Right? UAV just explores the entire environment and gives you, these are my outputs. Right? So that's what initially happens. And over time, sophistication will happen of the policy and it learns more intelligent behaviors. Right? So once these preferences are given, reward is computed. At the same time, algorithm is also run on a slower time scale. We call this faster and slower time scale. That is, with a smaller step size, it finds an optimal policy and these two complement each other. You improve the policy, reward is improved. You improve the reward, policy is improved. And if you run it ad infinitum, you will converge to an optimal combination of reward function and optimal policy, right? So how does it do? Just I was discussing, the preferences doesn't have to be 0, 1. Right? Of course, we have two distributions here. One is ground truth and one computed by the network. The logical loss function is a cross entropy loss. And that's what happens. You compute a loss. Mu's are the preferences given by the human. Right? Observe, mu1 can be 0.6, mu2 can be 0.4. Right? I can say, as he said, I'm only 60% sure this is good. Give it 60%, right? So, and this P hat is the probability computed by the algorithm. Right? It has a component of reward function, right? What is the probability that you prefer trajectory 1 over trajectory 2 is, what is the total reward you collect over the trajectory divided by total reward, right? So this loss function is a function of reward, right? By optimizing this cross entropy loss, it tries to compute a reward function that aligns with the human preferences, right? So this is the idea that has been used in PBRL. Of course, not our idea. This is proposed in the paper. We are trying to use it for our application, right? So we applied this for the problem that you saw. And of course, it did not work because things rarely work when you immediately apply. So, one problem which, of course, all of you would understand is sparsity, right? You can't collect everything in one go and so on. So of course, the logical next step was mixture of experts. The idea is where you train instead of one reward function, you train multiple reward and take consensus. No, that's a reward function. We don't have any reward function now. Yeah. You can randomly generate. If you don't have any preferences, you can randomly generate news. Yeah. Yeah, there is a way. So there is something called a synthetic or oracle reward function, which assumes that expert trajectories are known and provides mu's and mu and mu2. In fact, we had an experiment confirming that if you have an oracle reward function which already knows mu1 and mu2, optimal mu1 and mu2, whether this algorithm can learn that. In fact, we see it can learn to some degree. So I said, right, don't have to be. Mu1 can be 0.6, mu2 can be 0.4. Yeah, that's a new paradigm. Yeah. So this is currently working with only 2 trajectories, and why not? We can extend it to multiple trajectories and rank them. It's essentially ranking now, no longer preference, it's a ranking. So excellent question, right? You are essentially asking about generalization, right? So the thing is, you want UAV to learn that there is an obstacle. You don't want the UAV to memorize that obstacle is at this point, right? You are training the UAV to identify that this constitutes an obstacle. So you're trying to, I mean, of course, the end goal is to make it learn. Whether it learns or not is a different issue. But our goal is to make it understand that an obstacle looks like this. And if you take an action, you might get hit, right? So you are not trying to brute force it, right? Giving it, this is the position of UAVs or obstacle, so you don't go there. That's not. So even if it dynamic obstacles, dynamically changing, doesn't matter. Once it understands or learns to identify that this is an obstacle and I have to take an aversive action, it takes it. Excellent. Yeah. It definitely changed. I mean, if anyone use, I mean, of course, I have used ChatGPT. I mean, the results, if you see, you might not like it. Right? That's perfectly fine because the labels have been given by someone else. But take this application, right? We have a particular application in mind. The objective is to avoid obstacles, to pass through waypoint, and so on. So it is possible that most of us will have the same consensus, right? If it passes through this waypoint, it's good. Otherwise, it's bad, right? So, I mean, the numbers might differ. I can give 0.8, 0.2, you can give 0.6, 0.4. But the final objective would not be changed that much in this. But if you really take very subjective areas like this LLMs, it differs drastically. That's a very important problem. Right? So I didn't go into details of it, but I just want to show a video demonstration of this to probably convince you that this might work. So here, the objective here is to not just avoid obstacles, but retrace the path. That is, you would see a UAV taking a path and coming back in the same path. This is a very difficult problem using traditional reward structure. We don't even know how to postulate it. Right? Here you would see that, of course, it goes very slowly. Maybe I can quickly go fast. So it just goes, avoids obstacles. And it takes the same path or approximately same path back. Of course, we didn't measure it, whether it's exact dimensions or not. It's just a visual based analysis. I mean, we measured something else of performance. Yes. So here, all we gave was preferences. And based on just the preferences, the UAV has learned to essentially navigate in. And here you would see dynamic obstacle, that is humans keep moving. Of course, this is not a UAV environment. This is just for testing the efficacy of the algorithm. And here you would see that it does avoid colliding with dynamically moving. Right. In fact, one interesting part about it is while training, we trained only on 3 humans. That is, in the training simulator, there were only 3 humans who were moving, and we transferred it to the 4 humans just to see whether it generalizes and learns well or not. So that's what I said. So it's not just local information. We are not giving pictures and training. We are giving trajectories. So it does something to the end until it collides or until it ends. You like a video over the other. So that's very important. It's not, because as you said, if you're looking at pictures, it's greedy, as someone has rightly pointed out. Right? So it's a video versus video. Right? Yep. That's that. In fact, we faced it. So we broke down the trajectories into segments, the logical, meaningful segments, and then we ranked. So yeah. See, these are all the issues that you would face inevitably in a large environment. Here there was no objective. Here the only objective is to, in this, only objective is to avoid colliding with humans. That's an interesting question. So I don't know why it not stayed in the corner. That would be logically a good thing to do. But the way we give preferences is when it goes and collides with a human or about to collide with a human, you would say, I don't prefer this. I in fact prefer you moving around, not going closer to humans. And based on that, it has learned. It's perfectly possible that one of the policies that it would converge is I'll go and stay in the corner. It's perfectly logical, right? So many optimal policies or many suboptimal policies can be learned. And this is one that it has. That's a good point. So if I run the algorithm again, Am I sure will I get the same path? Of course, no. With one probability, no, because the preferences change, the way trajectories are generated will change and so on, right? So every time you train it, it changes. Maybe one logical policy would be staying in the core. Yeah. Exactly. So that's how it is operating. From the trajectories, you extract reward using the model which has been shown to you. And then using that reward, it learns a policy and this continues, keeps happening. And this is your final waypoint navigation where it just passes through this. Here there are multiple objectives passing through the waypoint. Yeah. Yes. Yeah. The state here is the depth map. Every time depth map of that's the input. So here probably it has gone through the waypoints. Right? It passes through all the three waypoints without colliding with any of the state. Right? So yes, this is after training. Very nice, sophisticated pictures. So during training, we'll see all sort of behaviors. So yeah, so that's that's what RL can possibly do, right? So you can train autonomously. Of course, not full. Human is always there to give a feedback, right? And based on that, the UAV learns to essentially navigate in that environment, right? So now quickly going into what is RL after seeing what RL can do here, right? So it's essentially a paradigm for solving sequential decision making problems. That is, as you have seen, it's not a single stage decision problem like you would take in other ML approaches. It's you need to take actions in sequence. Right? Yeah. Yeah. Yes. I mean, the algorithm that we use after computing reward is a policy gradient, TRPO. Yeah, TRPO. It's a paradigm for solving sequential decision making. That is, you take decisions over time to achieve a larger objective. So underlying construct here is what we call as a Markov decision process, where the next states evolve just based on the current state, irrespective of what the history has been. As the Markov process, we assume that that's how states evolve. Need not be true in real, but we just go ahead with it. And so the ingredients of this MDP is S, which is a state space. U is an action space, that is actions that you can take. Once you take a particular action in a particular state, you transition, right? You move to a different state. That is captured by this matrix called P, which is a transition probability matrix. Given a state S and action A, what is the probability that next state is S dash? R is, as we discussed, reward function. In traditional RL has reward function. We have saw an application where R is not needed. And gamma is what we call as a discount factor, right? So at this point in time, I want to maximize a long-term reward. So how do you capture the long-term? Right? You get reward R1, then you get R2, R3, R4, right? If you keep summing up, that's a long-term reward, right? But if you are playing this game infinite number of times, any sequence that you add up, non-zero sequence, will be infinity. So it doesn't make any logical sense for any algorithm to work. So we essentially use this concept of discount factor, which discounts the future rewards, right? Some intuition has been taken from economics and so on, where if I ask you if I have to give you 100 rupees now or 100 rupees after 10 days, we inevitably say I want it now, right? So the future rewards are always discounted at this point in time, right? So it works beautifully both mathematically, that is, it solves the problem of your long run infinite reward, as well as it makes some sense. Right? So our objective is to learn what we call as a policy. It's a function which maps a state, that is what you see, into what are the possible actions that you can take. This is a distribution over actions. So you can say I'll take action 1 with 0.6 probability, action 2 with 0.4, and so on. So your objective is to learn this pi that maximizes long run reward. And this is example I keep citing every time because it's so easy to understand. To understand what are the various parameters of your MDP, right? So let's say we want to have this problem of diabetes control, right? So what are the states? State is what is the current parameters of the patient, right? It involves the results of blood test, weight, height, thyroid, and so on. So these are the measurements that one would have. In this case, this will hardly be an MDP, but yeah, just to go ahead with, I think Yeah, this will hardly be an MDP because if I just don't care about my health now, it always going to be a effect in future. So that's a good point. It's hardly an MDP, but just for the sake of understanding this, let's go ahead assuming it's, I mean, hardly anything we do actually in practical is MDP, but we still go ahead and apply RL algorithm. Sorry? Yeah. So MDP is when, let's say you are at a certain state ST, the next state ST plus 1 should depend only on this ST irrespective of what your S naught is plus 1, so on and so forth. But we do know that, whatever we do now is going to have long-term impact in the future, right? Your further states, just given the previous state, is not independent of your all earlier states, right? So in that way, it's, yeah, of course, we didn't go ahead and apply in this application because of course it's not safe, right? So and so as both of you rightly said, right, this is just to illustrate what are the components of MDP, right? Not to actually model it and apply any algorithm to find an optimal solution. And here the actions probably is, what are the dosage of medicine that you would have to take, right, given the current parameters of the patient. And then we essentially transition, right? You take that medicine for, let's say, 1 month period, and then we move to a new parameters. Our blood tests change, our thyroid count change, and so on and so forth. That is the next state. And we incur a reward, right? The reward is how did the sugar levels change over time. If it increased, it's bad. If it decreased, it's good, right? These are your immediate reward. And of course, our final objective is to completely avoid or get done with this diabetes, right? So that is the total reward. Your objective is to go to a state where you are free of diabetes. So that's how these parameters play out. You will be in some state and we take some actions, we move to a next state, we collect some reward based on how good that action has been there in that state, and we keep collecting it. And we want to maximize this long run reward that we keep collecting over time. So putting it mathematically, we are essentially trying to maximize this reward R naught plus gamma R1. As I said earlier, gamma is a discount factor that discounts the future rewards. So this is the long run reward that we are talking about. And because this is stochastic environment, that is states are not deterministic, states are probabilistic. So you have a quantity of expectation which converts this random quantity into a scalar, right? And you want to maximize this particular quantity. And then thanks to the linearity of expectation, we can break it into two terms and then have the equation like this. And then this is what we call as a Q-Bellman equation. That is, you want Q of S comma A to be expectation of a reward plus gamma times max of Q of S dash comma B. This sort of formulation. Yeah. Yeah. Yeah, I think that case it's okay. But when I said the current, then it makes sense, right? So in that slide which I gave, it was only current parameters. So that doesn't constitute essentially an MDP evaluation. So whatever you said, if we take care of long-term dependencies and yeah, I mean, it learns, but the point is we can't, like UAV, we did in simulator, but here we can't do it on a patient. So that's a really tricky problem to solve. Yes, that's a practical problem. Yes. Yeah, so as we discussed earlier, we don't really have, in RL, we assume that we don't know the model, right? We don't have the access to this, probability transitions and reward function in its purest form. All we get is we explore something and we get a trajectory from it and we have to live with it. And that's when, we take this shift from traditional dynamic programming. I mean, essentially we can solve this using dynamic programming, right? Provided we can compute the expectation. So the problem is we don't know the probability values. It's not given to us. So one only has this, what we call as samples. That is, whatever state you were in, what are the action you took, and what is S dash. And it is true in the example we took as well, right? I mean, given the parameters, if we take some dosage, how we are going to transition depends on many, many factors. You can't deterministically put, like, this is the state of the patient in the next 1 month. It's always a distribution. We don't know the distribution as well. One that needs to be accounted for in our. So That's what an RL agent is. It maintains a decent policy. It explores this. Over time, it collects this, what we call as samples trajectories. It learns, okay, I see if I do this, this is happening. If I do that, this is happening. And using this particular inference from the rewards that it is collecting, it keeps improving the policy. At the end, it would finally compute the best policy or the optimal policy. So it works just with the samples. So that's the uh, process. And mathematically, how are we attacking it, right? So we don't know the expectation. So if you think, essentially we need to solve this equation, HQ is equal to Q, where HQ is this particular equation. And then, this is essentially a fixed point. Your Banach fixed point theorem will tell that if this function is a contraction, you have a fixed point, irrespective of where you start from. You start from any Q naught, you run the fixed point theorem, you are going to converge. That's so, provided this is a contraction, and it in fact turns out to be a contraction function. But now we don't know expectation. That's when the theory of stochastic approximation comes into picture. It says it's fine, even if you don't know expectation, treat it like a noise, and then go ahead with your updates. And that's how going from here to here is through the stochastic approximation language, which avoids the expectation. You can just freely work with the state action samples that we are getting at each time point, and still run our algorithm and converge. We are not running dynamic program. It's only on this sample. That's what is essentially the value iteration or policy iteration algorithm. You do run the algorithm at each time point and keep improving, just following this fixed point theorem. So that's what happens, provided we know the parameters. Yeah, that's my next slide. So essentially, that's what the next slide also talks about. When number of states and actions are very high, in fact, can be infinite as well, right? So traditional methods where we store this state and action values in a table becomes infeasible. I mean, we can no longer work with such a construct. We need an approximation architectures in such cases, right? So there, what we do is we essentially approximate the Q of S comma A, the construct that you want to compute and manage, approximated with this neural network whose parameters are theta. And your objective is to tune the values of theta, that is the neural network weights, in such a way that this Q of S comma A is very close to this expectation. So that's what naturally being done. So we take MSC loss between, of course, expectations are here, but when in practice you don't get it, we get only the samples from the system, and we do this particular update of theta, and this is your right hand term H of Q, and this is your current estimate, and you try to minimize the distance between these two quantities. And if they are closer enough, we are good, right? So we run this until infinity, and we tune the weights of neural network to make sure these two come together, right? So that's what typically one of the algorithm called deep Q learning tries to do in the practice, right? So what are the challenges, right? So challenges faced by traditional RL. One thing is what we call is off policy. That's what I plan to discuss in the next slides. I'll try to put it in time. So where essentially think of it like currently the agent is exploring on its own, deriving trajectories and improving. But as we discussed, as have been discussing, this exploration is not easy. It's not safe sometimes. It's very tricky and very difficult, right? So the question that we ask in off policy is, given trajectories from some other policy, right, historical data or data which is there, using that data, can I work with RL algorithm and improve, come up with optimal policies, right? If we want to think about it, right? So the example that can be thought is, suppose we go to restaurant which you have never been to with your friends, but your friends have been there to the restaurant. Then you ask them, do you like this item? How do you feel about this item? If they say, right, they have been your friends for a long time, right? If they say it's very spicy, for you, it might not be spicy, right? So you can gauge, right? Okay, your friend is deriving from some distribution and you have your own distribution. You can mix and match that and try to come up with a consensus, right? We ask multiple friends, okay, what do you think? Do you like this item? They say, I think this is very spicy for me. But you might think that because you know the tastes of your friend and how he or she behaves, we can deduce that probably this is not spicy for me. I can go ahead and order it. So it's such kind of paradigm where your trajectories, samples are coming from a different policy, and you're trying to find optimal policy using that instead of you exploring directly, right? And there are other problems faced by standard RL, like multi-agent settings. How do we extend it to multiple agents, because there, along with traditional problems, you have the coordination issues. And then how do we apply to real life? Just now, as we were discussing, the example which we took was not, MDP. So typically we encounter applications where there might not be Markov process. How do we deal with it? How do we take partial observability? So all these issues come up when you try to go ahead and apply in real life settings, right? So off policy control, I'll quickly go through this given the time. I'll give you quick pointers and important pointers in this research area. So here our objective was to build an RL algorithm which is convergent, efficient, and flexible. So we will come to know in what sense do we mean convergent, efficient, and flexible. So for convergence, what we want the algorithm to converge, right? Essentially, we all know that in deep neural networks, when we use it, they are prone to diverging and some things that you can't control. And off policy RL inherently has this problem of divergence. That is, there are papers which prove that, if you have the off policy bootstrapping and so on, it will definitely diverge. It's, so we have proof saying algorithm, I am showing you scenarios where this can diverge, right? And so convergence is a very big problem in RL, especially when you go to neural network setting. So that's what we wanted to address. We want to come up with an algorithm which has good convergence guarantees. And then we want generalization, of course, because we can't train on infinite number of trajectories and samples. And then we want quick convergence, right? If it converges but at a very, very slow pace, then it's essentially not very useful to us. So we address that using the concept of natural gradient descent instead of standard gradient descent, right? And this we saw works well in on policy, and then we extend it to the off policy set. So this is what we call as a policy gradient. We have seen deep Q learning. Now a different paradigm of RL is policy gradient, where we define an objective of this, and we want to find, first what we do is parameterize the policy. That is a function which maps state to actions. And then you want to find a parameter theta, which maximizes the objective that you have. This is a long-term objective. And you want to find a theta star, which is an argmax of this particular function, j of theta, right? So this is typically done using policy gradient algorithms. And a very seminal result in RL is coming up with a closed form of this gradient, because the problem is clear. We want to maximize this j of theta, and maximize this j of theta, and first step is calculating the gradient of this. Once you calculate it, we are done, right? So seminal result around 2000s or 2001 is coming up with a closed form. Researchers have done great job coming up with this. And of course, here again, we don't know expectation, we approximate it and more, right? So, let me skip that. I'll just show you an architecture and show some results on that. Traditional actor-critic, what we call as algorithm, which is used to solve policy gradient, has an actor who performs actions, and then there is a critic who gives a feedback to the actions that has been collected, right? So you perform certain things, and then the critic says, I think this is not good, this is good, and so on. So this is what is called as actor-critic paradigm. There the issue was, if you take traditional actor-critic with arbitrary architectures, that is both are neural networks and independent, then it works. It is unrestrictive in the sense it generalizes well. Good results have been seen and applied well, and so on, but it doesn't converge. We don't have a convergence guarantee. Now, if actor and critic has what we call as a compatible architectures, that is, they share some of the weights, some of the features, then we have convergence. But unfortunately, the result, traditional result says the approximation can only be linear. That is a very restrictive space to work with, right? It's very difficult to generalize, even though in theory it has good guarantees. Now, we want to get best of both worlds. We want convergence, and at the same time, we want to be generalizable as possible. And that's when we said we will have an additional critic, right? And one critic, we gave the full capability of generalization. To the other critic, we said, be compatible to the actor and perform your updates. And that's essentially, in essence, that's what happens. I plan to show through equations, but let's just skip. And that's what happens in your on-policy algorithms that we have. And natural extension is extending it to the off-policy setting, whereas I said states and actions are coming from a different policy, right? And I just show one slide and we will end there. So this is the typical policy gradient, notice this distribution of states, right? D, tilde, pi, and pi. But now your actions and states are coming from a different policy called mu, right? And I want this term in function of d mu and d pi, right? Because your actions and states are coming from different policy. So the beautiful thing is here is we just multiply and divide. Essentially, we multiply and divide by d mu of s and try to estimate these two quantities. And fortunately for us, when we are doing this research, researchers have already worked on estimating this ratio of stationary distributions pretty independent of RL, right? So there are algorithms which have been trying to solve only this problem. How do I compute a ratio of stationary distributions from samples? Beautiful problem that has been solved, right? So we just took that intuition, we took that work and incorporated in this work for our algorithm. That is, how do I find these ratios? Because if I do that, we are done. So we have the algorithm which can use states and actions from a different policy and still work well and gets the optimal policy. So that's what happened here. So if you see this figure, it's again still 2 critic and 1 actor, but augmented with this distribution network. So this is not our work. So this is taken from literature, the researchers who have already developed how do I estimate the ratio of distributions. And that augmentation is given to this algorithm, the critics, and then they work for the off-policy case as well, right? And yeah, these are the results. We tested on a pretty basic small environments like a cart pole, acrobat, mountain car, and lunar lander, and saw decent results. I won't say these are exceptional results. I mean, you can see that the difference is not much high, but it has some good convergence guarantees and so on, and seems to do well more in off-policy settings. That is, an off-policy setting. It's not exactly, but it of course uses the concepts of metropolis, but it's not directly that. So it extends from there, it builds up from. Yeah. So the x-axis is the episodes and y-axis is the total reward. And the blue curve essentially shows that some cases it goes faster compared to traditional. Yes, each episode starts and ends. For example, in cart pole, if you can make the pole balance for, let's say, 200, then it's a success, independent of it. So this is not growth. So in each episode, what we are plotting is episode versus what is the reward accumulated. Initially, you would see pretty less, right? So it's here, and over time, it learns. So all these episodes, you would see higher rewards. So it's not a cumulative reward. It's just independent reward at each. Yes, ending is good. Convergence improves. Yeah, I mean, you have convergence guarantees with having 2 critics. Okay, but what do we do with that is not clear. Probably, it can improve the performance, but what each critic does is not clear. How do? Yeah, that I wanted to discuss, but I don't have time. Probably I'll take it offline for that question. That's the whole point of this discussion anyway. So in off policy, we can see, yeah. Any question? Oh, no. In off policy, we see improved results. That is, we see the results better than in the on policy case. And I just want to end this with a video. I mean, we can just not worry about it, but yeah. So this is and this is just a demonstration of how it learns over time. As you can see, of how it learns, right? Initially, you would see that it's just explores, it falls down. Because it's a simulator, it's okay. Don't worry. So it just falls down. And one more disclaimer is, this is not exactly training. We put together multiple phases of training. So don't think that it learns so fast or it is so good. We just put good clips together, right? So this is not entire representation. So now you see that, the objective is to come and stop between these 2 poles. So it finally learns to do this, right? So earlier you would see that, so I just want this data point here. Okay, It does, but it does pretty slowly initially. I mean, probably I missed explaining that particular portion. So here it's crashing and completely crashes. This is training. This time it goes away because these are all exploratory actions at the beginning, right? So sometimes it doesn't even come out like the case which you said, it just goes into the corner. And over time, the performance improves and, and here again fast. Now it is coming down. That is in fact true. So here it has come down safely, but it was very slow. Now you would see that it has come down pretty quick in between these two. So that's what overtime training does to this algorithm. Yeah, so that's all I have. Yeah, these are from these papers, parts of these papers. Thank you.
So thank you, Professor Raghuram, for a very interesting talk. Any more questions, are there?
It is not incorporating, but yeah, that's a very good question. I think we should explore that, how it's doing.
They were claiming even if everything fails, they'll still land. That's what I read somewhere. Okay, thanks everyone for attending. Yeah, thank you.